Our project introduces a modular nano hydroelectric generator integrated with Internet of Things, or IoT, management, alongside an automated dual-source power transfer control system. As global electricity demand rises, the reliance on non-renewable energy sources poses significant environmental and reliability challenges, especially for remote and off-grid communities. To address these regional energy deficits without requiring massive infrastructure or large reservoirs, our team focused on small-scale, run-of-river hydroelectric technology. This prototype is designed specifically for lining irrigation systems. By simply setting it up within the irrigation lining, it harnesses the flowing water to generate clean electricity. Let's examine the mechanical design of the prototype. We utilized a modular approach to ensure ease of installation in remote areas. The physical structure is constructed primarily from PVC materials. We used this for both the penstock and the turbine housing because it provides a lightweight yet highly durable modular framework. At the core of our hardware assembly is a three-phase, 24-volt permanent magnet alternator, or PMA. This alternator is mechanically coupled directly to the turbine shaft. As the irrigation water flows, it rotates the modular turbine, which in turn drives the PMA to produce raw power. Because this system operates in a wet environment, we utilized industrial-grade materials to enclose and protect all sensitive electronic components from the elements. To achieve precise system monitoring, we integrated a custom, specialized sensing suite into the prototype. First, for flow rate measurement, we developed a custom-built two-blade turbine flow sensor using an inductive proximity sensor. This component measures the RPM of the turbine blades, which is then algorithmically converted into real-time flow rate data. Second, to monitor current, we implemented an ACS712 current sensor. This allows us to measure both the AC and DC current fluctuations within the device. Third, for voltage monitoring, we utilized a voltage divider circuit to track the DC voltage output. We also integrated a ZMPT101B AC voltage sensor to measure the AC output parameters of the system's inverter. Finally, for power conversion, the rectified DC output generated by the alternator is stabilized and then converted into mains level AC voltage using a DC-AC inverter, making the power usable for standard applications. All of this hardware is managed by an intelligent control unit. The central processor of our prototype is an ESP32-based system. To ensure continuous monitoring, even during hydrogeneration interruptions, the ESP32 is powered by a dedicated battery. For the local user interface, system parameters including real-time voltage, current, and flow data are displayed on an LCD screen equipped with push buttons for manual navigation. However, a key feature of this prototype is its remote capability. We integrated an IoT module that allows for mobile-based monitoring. Through the app, users can remotely check the generator's health, monitor the hydraulic flow rate, and track the overall electrical performance in real time. In practical applications, water flow can fluctuate due to environmental factors like debris fouling. To ensure continuous power availability, our power management architecture features an automatic transfer switch, or ATS. We implemented this ATS using a DP-DT relay to manage transitions between our Nano hydrogenerator and backup grid power. The system uses smart logic to constantly evaluate the real-time electrical and hydraulic parameters. If the water flow drops and the generator cannot sustain the load, the system seamlessly switches to the backup grid. Once optimal flow returns, it transitions back to the hydrogenerator. In conclusion, this modular nano hydroelectric system, with its automated dual source transfer and IoT integration, is designed to be a scalable, sustainable, and reliable energy solution for remote deployment. Now, let's walk through how the prototype is deployed and operated in a real-world setting. Setting up the system is straightforward. Because of its modular design, the entire unit can be transported easily to remote locations, such as the agricultural irrigation sites in Bans Allen Site 1. To deploy the device, you simply position and secure the PVC penstock and turbine housing directly into the flowing water of the irrigation lining site 1. No massive civil engineering, large reservoirs, or deep excavation are required. Site 1. As the water flows through the channel, it naturally engages the turbine blades. Once the system is placed in the water, you can observe its operation locally or remotely. On site, technicians can use the push buttons and the LCD screen to instantly check real-time metrics like voltage, current, and water flow rate. Site 1. Meanwhile, the ESP32 microcontroller continuously packages this data and uploads it to the IoT mobile application. Even from a distance, operators can pull out their phones to monitor the generator's health and performance. Site 1. If debris builds up in the water or flow rates drop, the automated power management architecture takes over instantly. Site 1. The automatic transfer switch, driven by the DP/DT relay and smart logic, seamlessly shifts the load to the backup grid, ensuring uninterrupted power delivery before switching back automatically when normal water flow is restored. Site 1. This plug-and-play approach makes the Nano hydrogenerator practical, efficient, and resilient for rural deployment. Site 1.